Okay, so we're online? Not online, but we're recording. And I went ahead and updated your syllabus, and did not burn a copy of it for you, but here it is. So you can look at it and you can see it. Right here. So we are at 4:09. We're going to get through chapter 3 today. Did everybody know that we're going to get through chapter 3 today? We're going to work on chapter 2 problems, and we're going to get into chapter 3. And you're supposed to hand in the Bodhi plots today, and you were supposed to hand in did I say the conduit fill counts as quiz 6. That one is to be handed in as well. So conduit fill and Bodhi plots, hand those in. Problems due at the end of chapter 2, problems at the end of chapter 3. Excuse me, problems into chapter 4. We'll go through chapter 4, and on the 21st, we'll have a general review, and then we'll have our exam 2 in class on the 23rd. On the 28th, 8 a.m. to 10 a.m. here, we will have our final, which will be comprehensive, and you'll be done. Oh, and by the way, you have to hand in lab 9, 10, and 11 as well. 9 is build a circuit. It counts as 3 labs. So that'll be 60 points. Number 10, we'll go through that in class. It's the same as circuit with the PLC. Lab 11, which counts 20 points, is prove to me that you clean everything up. So that will be an additional lab. It will be, you'll have to do all these by Wednesday of finals week. So if you're worried about how long, I give you plenty of time, but they have to be done by high noon Wednesday of finals week. So I have time to grade and get that all taken care of. So it's all published and it's all right there. So if you wonder what we're doing and how we're doing it, this is the syllabus. Any questions? The syllabus lays it all out for you if there's any questions. You got some things to do. All right? Any questions about that? Everybody soak that up and ready to proceed, right? There's a lot there. It's doable, but there's a lot there. Okay, you're going to be working on that little thing that goes back and forth for a little while. It's very doable, but it's going to take a little bit of time. Enough. Okay, so let's go back and look at chapter 2, which is semiconductor devices. Thank you. Thank you. I'll get this stuff taken, graded for you back into you. Okay, so this is semiconductor devices. Two. So basically, all the problems at the end of chapter 2, 3, and 4, that'll be easy enough, right? They're not very hard. These are pretty simple questions, really, and they're not no, they're not very hard. How's that? So let's work through some of these at the end of chapter 2, and then get on to chapter 3. Thank you. So here, you're looking at a problem, a simple diode problem. Determine the circulating current if it's 6 volts and the resistor is 10K. So basically, you have to ask the question, which of the three models are you going to use? And typically, you use the middle model, which is what? What's the middle model? Middle model is a zero point 0.7 volt drop in voltage, and if it conducts in the forward direction, there is 0 ohms, okay? That's 0 R, 0 resistance. So if that's the case, and we got 6 volts, we have a diode, and if it's over 0.7 volts, it's going to flow. So basically, if you have to ask the question, is the forward bias over 0.7 volts? And if it is, then you're going to have a forward bias. So this will soak up 0.7 volts. So what do we have over here at the resistor? 5.3 volts. So what's the current? What's the current through a 10K resistor? I don't know. That's got a diode in it. There's nothing hard about this. This is resistive circuits all over again. All right. What is it? It's 5.3 divided by 10K, or 0.53 milliamps, right? Is that right? Everybody agree? Any problem? Now, if I insert the diode in the other direction, current cannot flow this way. It's got to flow this way. Therefore, it's blocked. So what is the current then? I equals 0. This is the example of the little dog door opening, and now it's closed and it will not work. So there's your answer for number 2. Number 3. Here we're given the same problems we were before, except for now what? 12 volts. We've got 2 resistors. And they're both in the forward direction, so it's going to flow through them. They're going to let it flow. But what is the voltage across that? 0.7 volts. What's voltage? 0.7 volts there. So what is the effective voltage around the circuit? It's 12 minus 1.4, or it is what? 10.6. So now you use 10.6 volts, and then you have these resistors in series. One is 4.7 K, and one is 3.3 K, which totals up to what? 8 K? You got 10.6 volts, 8 K. That's what you go to war with. 10.6 divided by 8 is equal to what? 1.325 milliamps. Right? That's all it is. You just got to watch which way the diode is directed, and you're all set. Now, this is a little bit more difficult, but not by much. Here, we're saying, okay, I've got 10 volts, and I've got 2.2K, and I've got a diode, which by definition is 0.7 volts, because it's forward biased. I got 10K over here. What is the current through these devices? What is the current around this device? Now you've got to say, okay, what is the current through here at what? What's the voltage across the 10K? What's V10K? 0.7 volts. Why? Current around in a closed loop has to add to 0. So if it's 0.7 here, it's got to be 0.7 here. Any question about that? So what's the current through the 10K? 0.7 divided by 10K. 0.07 volt, or 0.07 milliamps. Everybody see that? What's the current through the 2K, 2.2K? Well, I've got 10 minus 0.7, or 9.3, divided by 2.2K. What is that? 0.22? 4.23? 4.23 milliamps. Now, what is the current through the 0.7, or what is the current through the diode? I of the diode is equal to what? 4.23 minus 0.07, or 4.16, something like that, milliamps. Did everybody see how you play this game? Any problems? Any concerns about that? It says, determine the voltage drops across the resistors. All right, what's the voltage drop across this resistor? They don't ask for the currents, but I just solved the whole question for you. I just solved the whole thing. I basically did all the stuff that he didn't ask. But the voltage drop across this resistor is 9.3. The voltage drop across this resistor is 0.7. So now you can figure the current. You can do the rest of it. He didn't ask you what I just did. I did the whole problem. But anyway. Determine the LED current. Assume the LED barrier is 2.1 volts. Okay. The source is 5 volts and the resistor is 330 ohms. So basically, this sucks up 2.1 volts. Oh, by the way, the other day, the guy I couldn't remember, you probably don't care. I guess I don't care either, but I'll tell you who his name was anyway. The guy that invented the integrated circuit. Now, this is kind of one of those that he kind of invented this integrated circuit. So there were two guys that invented the integrated circuit. One was Jack Kilby. The other guy, I forget his name, but he worked for Fairchild out in California. So this guy was in Texas. This guy's in California. This is what set up Silicon Valley as, this right here, this guy and this invention set up Silicon Valley as the place that people went to work on computers. This is how this guy in Texas was. And this is the guy that was a hero where I went to school. He was the man. So he went to Illinois undergraduate and whatever he did also, whatever. But anyway, Jack Kilby. He was just more like everybody else, but he stumbled onto the integrated circuit because he hadn't worked for Texas Instrument long enough to get a summer vacation. Everybody else got a break in the summer, and they got I guess a month off or whatever. He was stuck in the office. He just putzing around, and he found out how to make an integrated circuit by putting capacitor, a resistor, and an NPN transistor combined on silicon. That's what an integrated circuit does. So that's how they did it. That was in 1958, 1959. A long time ago, but it's not that long ago. I was alive then, whatever. Beside the point. But I was around then. But that was, and this guy here, he did the first practical one. This guy did the first one, but this guy did the first one that was commercially practical. All right, enough on that. This guy, let's go down here, 5, and determine the LED current. This is a little bit different because the barrier is 2.1 volts, so they give you that, and the voltage here is 5. The barrier voltage, in other words, the voltage across this guy is 2.1, and the resistor is what? 330. So you subtract 2.1 volts off of 5, and that gives you what? 2.9 volts, and you get 330 ohms. What's the current? It's 2.9 divided by 330. 2.9 divided by 330 is equal to what? 8.78, right? Milliamps. All right. And if the LED is inserted in the reverse direction, it is 0. Number 7, determine the resistor current in figure 236. The source is 15 volts. Okay, so you've got what? Well, this one doesn't count. Why doesn't it count? Because it's reverse biased, but you're going around it, so you don't really, it's like an open circuit. So it really doesn't count. This guy is a flyer. It doesn't really matter. Okay? So we've got 15 volts. We've got an R1 of 8.2K. And we've got a backwards, which basically is an open circuit. And then we've got a resistor over here, which is 3.9K. And I've got a diode in here. So what does the diode do? It drops at 0.7 volts. So you now have 15 minus 0.7 is 14.3 divided by what? 3.9 plus 8.2, or 12.1. So what is their current? Current is flowing this way. .18 milliamps. .18. Number 8. All right, now we get into a little bit different here. This is a Zener. Now, when you do this, when the Zener is pointed forward, it acts like a regular diode. When it's pointed in reverse, it actually chews up that amount of voltage. So basically, it still conducts, but it chews up that amount of voltage. So let's just go back and look at Zener diodes for a minute, because they're a little bit different than, because it's got the little curly thing on it, it makes it a little bit different. Let's go back and look at them in the chapter, because this is a little bit different application. Okay, so let's go back and look at Zeners. The Zener diode, it behaves like an ordinary diode when forward biased. Normally, though, Zeners are used in a reverse bias direction. The reverse is high enough, a diode can go into breakdown. Okay, so this breakdown is a bad thing, except for Zeners. And in Zeners, if you have reverse breakdown, you actually can use them as a voltage source at that value. So the Zener diode takes advantage of this in order to produce a stable voltage. Zeners are specific by their reverse potential and are designed to handle larger currents and power than the average signal diode. And the Zener voltage is measured as I Zener. The Zener test current, a lower current may not fully push the diode into conduction, resulting in a lower. Now you can burn these up if you go too big in the reverse direction. An open switch when reversed, instead we model it as an open when its voltage is less than the rated and as a voltage source equal to the rated voltage if it is in the reverse direction. So in other words, here is the example. You always need to look at an example of a Zener, okay? Also find okay, so assume the power supply is 9 volts. If the Zener is 5.1 and the resistor is 3.3, the I is 9 minus 5.1, and that's what you have to do for this. Just choose up 5.1 volts, okay? So there's your answer for this one. Any questions about that? So that's how it's done. So we go back to number 8, and it is right here. So we're working through problems, the end of chapter 2, that might appear on a test that you might be taking at the end of whatever. So this is where we're at. These are not hard questions, but they offer some new stuff that we haven't done before, and they get you into the electronics part of this course, or this program, all right? So, in this case, it acts like a regular diode, right? It acts just like a regular diode. So 9 volts, and it does nothing other than the 0.7. And here's my resistor, 1K, this is 0.7, 1K, Ted. So it's 8.3 divided by 1, or 8.3 milliamps. Number 9. Now we have the 8 volts, the 5.1, and the resistor. So this chews up 3.3, and this is 10K. So we have 8 minus 3.3K, and now that is what, 4.7? No, 4.7K. 4.7 volts divided by 10K is 0.47 milliamps. All right. Here we have, this is an interesting one, because number 10, this assumes a value of what? $6.8. So now we have 9 volts. We have a R1 of 5.1K. This is sitting there like a power supply of 6.8. All right? So we now got a power supply of that, and we've got a voltage across it of what? Or current across it of what? 33K. Okay? Now, no current is flowing this way. This is not going to be supplying any current, but it's supplying voltage. So the current through here, well, there is some. The voltage across this is 6.8 by definition. So what is the voltage across this? It's got to be 6.8. It's what? Well, 206 milliamps, right? So what's left? 9 minus 6.8 would be 2.2. And what is 2.2 divided by 5.1? is 0.439. So I've got 0.439 flowing here, and I've got 0.206 flowing here. So what's flowing here? What's left? So I've got 4.439 minus 0.206 is equal to the I through the zener. And it's flowing in the direction, it's flowing down. Okay? Looks weird, but it works. So it actually is letting current go through in the reverse direction. But this is sitting there at a voltage of 6.8. So you use the 6.8 to find the current through this, but then you say, but there's current flowing through this, and what is that current is what's left. Any questions about that? 0.439 minus 0.206 is equal to what? 0.233 milliamps, okay? So now you've got some questions that you can review, look at. That's how they're done. Please hand those in, or hand in equivalent questions that, just hand those questions in. I kind of work through them, but you can work through them as well. Make sure you can work problems like this. Chapter 2. Here's the dog problem. Here's the dog thing that he talks about. He actually talks about it. It's kind of neat. Here's your dog, the dog doors, okay? Now, chapter 3 is on applications, and you say, we're already into chapter 3. We just started this. Yeah, I know. We go fast for a while, and then we slow down, so don't worry about it. We're only going to go through chapter 4, so we're not going to go that far into this book, but we are going to do we're going to learn enough that you can actually do some circuits if you want to. And you will use this in building the project that you're doing with the reciprocating, the linear actuator, okay? How's everybody doing with the linear actuator? You got it? You're kind of halfway, or three-quarters of the way, or two-thirds of the way? Is that interesting? Some people are not saying anything, some people are kind of grimacing, and some people are saying this, and everything in between. Good. Okay. By the way, we got a couple minutes. I want to show you how easy this is with a PLC. Is everybody ready for this? I've been itching to show you this for the last month, so let's just go ahead and break this down and show it to you. Okay, this is how you do this with a PLC. And again, I'm going to use version 20. You're going to be using version 16, so there's a few little caveats between the two, but I'm going to show you the basic program, how easy the program is to write. So you have to create a new project. In this case, we'll call it project 41. All right. And you go to project view. You can do this with the Allen Bradley or the Siemens. I'm doing it with the Siemens right now because I do not have the licensure for the Allen Bradley, but anyway. Add a new device. And you're going to find several new devices that you can add in. But it's under the controllers. It's the 1200, S7 1200 CPU. And you are either going to find a 1214 DC, 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 or a 1215 DC, DC, DC. I want to use a 1215 DC, DC, DC. They are the same, identical, except for a few little caveats. And I'm going to pick the second one, and I'm going to pick version 4.7, although you might pick 4.6 or 4.2 or 4.0, and I'll help you with that. I'll help you get started. This is the hard part. But building the program is rather easy. It really is easy. Okay? Now, in the news, you have to do all this do the check marks, and I apologize for that because you don't have to, you don't see this in yours, but uh, so anyway, you got to do all this stuff, and you don't have to do that. So anyway, you don't see all those screens, thank goodness. Now, some of you are going to have to fill in this little guy right here. Others of you are not, but that's another step that I'll help you with, and I'll help you get started with this. But after that, you come over here under Program Blocks, Main, which is OB1, which is your main area to program in. And now you have a programming area, and you have to get started somehow. But basically, you're going to have a bit that says, are you moving left or are you moving right? And when you are this would be this direction bit, okay, the dir bit, and it's a tag, and you have to click on it, and then you say define tag, and it is not a local. You never make them local. You make them globals, and you define it, and now it comes in as that. Now, if the dir is on and the limit switch is made, okay, let's just call this LS1, limit switch 1. All right. This would be a I, but we're just going to call it right now an M because it's coming in as an input, but I'm going to use it as a memory bit. This would be limit switch 1. Then you go through a timer, TON. This is the timing. This is the whole thing you were building that timing block for. And you put a preset in there of like 2 seconds, which is 2000. Okay, that's all you have to do. And that's it. And this would be, then you would have a bit that would come on at the end of this, which would be, you can say the timer, I'm going to give this a name, timer 1. Let's call it timer 1. Okay. And you click OK, and now you've got timer 1, and you're all set. Now, when this happens, this turns dir off, and then when dir is off, you do the same thing in LS2, and it turns it back on again. So you come up here, click on that, and then you say, when dir is off, is off, and then you put the limit switch in again. Now this is a physical limit switch 2. And right click on that and define tag, and you make it a global again. Define, then you bring another timer in. We call this timer 2. And click OK. And again, put the 2000 in. If you want a 2-second timer, you put in 2000. If you want a 3-second timer, you put in 3000. And now you put in the dir block, which should be the, okay, so you have a seal circuit, or you can use a set reset. Okay, how many of you like seal circuits? How many of you like set reset? I want to do it with set reset because that's the other way of doing it. You can do it with seal circuits or you can do it with the other. I don't care. Let's go up here and find basic instructions. Your basic instructions, you have right under instructions, you have basic instructions. Okay, so up here under instructions, you have favorites. Okay, you have general, you have bits, and then you have timer. And we're going to choose now under the bit, we're going to choose a set reset, which is a block. It's a block. Okay, so we're going to choose a block here. Okay. Now, before that, we're going to put a contact which says what? One that says timer 1.q, which is the output. Timer 1. .q, and the reset, which is timer 2. .q. And this bit will be my dir. My dir bit, okay, the direction bit. So if it's going one way, it's on, and the other way. Now you use this dir bit as an output to turn on an output when the dir bit but not the timer is on, or the not dir bit but not the timer is on. So it basically is a my output that goes the one direction is in the forward direction. It's dir, but not T1 dot timer 1 dot in. Now this would be forward. This is the one direction. Let's call it forward. That's the output, and that's, I'm going to make it as I'm going to define it as an M, but you would define it as an output. Okay. All right, and the not of the dir. Oops, excuse me. But not timer 2. Dot in would give me my reverse direction. And that again would be an output. That would be a Q, not a whatever. And this would be not a dir. Okay, that's it. You'd make this to your forward contact, this to your reverse contactor, and you're done. Okay, so this is on the video today. You can look at it. If you want to use this, you can use it. If you don't want to use it, you don't have to, but this will work. Any questions? Any comments? So this is after you've done all the work that you did, this is the other way of doing it. Is anybody crying yet at how long it would take to do that? Any questions? Any comments? All set? Good. All right. I've been itching to do this, so now I've done it, and we're back to normal. But I want you to understand that that's the after you've done it the other way. This is waiting for you to do it this way. And it convinces you, maybe, I don't know, maybe you will not be convinced, but I think it should convince you that the easy way to do things is with the PLC. It's the easiest and the best way to do things. It's the way that most people accomplish most of their tasks is to do it like that. All right, so now we're talking about more things you can do with diodes, and we're into the last part of the diode world. Okay, so what can you do with diodes? Well, you can make them into all kinds of things, and one of them is rectification of AC back to DC. And this is called half-wave rectification. And what do you have when you have this? What does it look like when you do this? It looks like the green. It cuts off a little bit of the top. It cuts off all of the bottom. So there is no negative side. In other words, your output to this thing looks like this. Blip, 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 blip. That's zero. That's supposed to be zero. It doesn't go up. It should be zero. I should draw it again. Should make a good attempt at drawing this, but it basically cuts it off. So half-wave rectification looks like this on an oscilloscope. What did you just do? You cut off half your waveform, and you decrease the positive waveform by 0.7 volts. All right? So that's what you did. And there it is. There's a picture of it. Okay, so what do transformers do? Well, transformers basically decrease or increase your AC voltage. So this gets you to a level, and then this clips it off. And what does a capacitor do? Well, now you have an RC time constant. And the RC time constant basically takes you like this. It starts to go down, but it doesn't, and then you do it again, and you do it again, you do it again, you do it again. And the bigger the capacitor, the higher, the less decay you get. So in other words, a really good rectification looks smooth, but it's never really, really smooth. It's always got a little bit of a dip because you're losing a little bit, but not much, okay? So here's zero, here's your plus, and it goes like that, and that's your rectification. Now, how do you improve on this? How do you improve on this? You do full wave, okay? Now, what does full wave rectification do? Well, it does every hump instead of every other hump. Okay, but what does it do bad? It drops you, instead of 0.7 volts, it drops you 1.4. So you get a little bit and you pay for a little bit. So you get a little bit and you pay for a little bit. But that's about it. That's all it does. And this comes out, and then you smooth this, and you're in. So this is full wave rectification. The other is half wave rectification. And basically, that's how it goes. So that's how you build a power supply. So that's a crude power supply, but it works. What's a better power supply? One that has a sensing device that if you open, or excuse me, if you short the output, it goes to what? It crowbars to zero. So that's the kind that we have. But this is the crude kind that it won't blow up, it'll blow a fuse. This is the first attempt at a power supply. This is not the cool ones that we have now, but ours have a sensing device on them that allows you to short the output, and they call it crowbar to zero. The crowbar effect that goes to zero. Okay? But they all have this in them, this kind of circuit. But the new ones are the better, not the new ones, but the better ones have the crowbar circuit in them. Okay, so that's pretty much all you have to do. Your RC time constant is a time constant that gives you how much flutter or how much decay you want, how much down you want, and you're all set. Okay. Any questions at all about any of this? So this is plus and minus voltage. Oh my goodness. So you can do all kinds of stuff with this. Now this is Zener regulation, so it gives you the ability to have a value out here that gives you a specific value of an output. Even though you start with a higher voltage over here, you can have the value of the Zener in here. And this works as long as you don't overload it. So if you need 6 volts and you only have 24 volts, you can put a Zener in, and sometimes it will work just fine, other times it will blow up because the current is too high. So you got to be careful with Zeners. Usually if I have to do something like that, I'll just put in another power supply. I don't mess around. I just put another power supply in. But if you need 5 volts and you got 12 volts, the Zener sometimes will work in this configurations. 5 volts. If it's a 5 volt Zener, then you can usually use it. If it's just a little bit that you don't need a lot of current for, it'll work. So anyway, what kind of problems can you have? Well, you get down to these, clippers and clampers. I always laugh when I see this section because clippers and clampers is kind of like it's kind of like the beginning of a vaudeville show or something like that. You're going to be talking about clippers and clampers, but it really does have, all these are good test questions is all they are, okay? These are not things that you would typically build, but they are son of a gun, really good test questions. Well, how would this work? Or how would that work? Or whatever, all that kind of stuff. Well, here they are, clippers and clampers, okay? How about something like this? What's the V out? Oh my goodness, you'd have to figure that out, and you do, and it works, and it's a clip. This is either a clipper or a clamper. I think this is a clipper. Okay? These are puzzles, is all they are. So clippers and clampers are puzzles. Okay? Everybody likes a puzzle. Not really. But this is the last gasp of diodes. Something you'll probably never see again with diodes, but they make good test questions. Okay? Therefore, you have 3 or 4 sheets, right? I would write every one of these down on that sheet. Because if you get into a test and you start to flutter and you wonder, now what's he doing now, or how's he tricking me now? You're going to have half a dozen examples, and it'll fit one of those examples. It may not be exactly the same number, but it'll fit the example. So my recommendation, my strong recommendation to you is regarding clippers and clampers, every one of these examples, every one of these homework assignment problems that I give you, write it down in a small little corner of your 4 sheets of notes that you can bring with you to your test. And when I put something like this on a test, you just sort through until you find the one that it looks like, and you're done. Okay? My strong recommendation is that, because in the middle of a test, your mind may blank out. It may go, however, and I don't want to see you suffer any more than necessary. So, I do want to see you succeed. How's that? So I want you to get these, but I also am warning you that in the heat of the battle, which one is it? Oh, it's like that one. Oh, and that's how you solve that one. Bingo, done. You don't have to worry about it because I'm giving you that capability. You can organize yourself and 3 or 4 sheets of paper, and if you don't want to, buyer beware. These are not easy on the spot to analyze, okay? But they're all doable, and you can figure them all out. They're all there. You can do them all. Every one of these questions you can do now if you just sit down and think about it. But in the middle of a test, your mind clicks. The things that you've done before are automatic, but the other ones, you're some of you do quite well. Others of you, and I do this too. I'm not talking to anybody but myself. Your mind starts to race, and you wonder, now, what on earth does he do? And until you get back to normal, and you think, oh, that's what that is, then you can do it. I'm not going to ask you anything more difficult nor different from in these problems in this chapter. That's all it is. Won't do it. Okay, so that's it. Clippers and clampers. The clodhoppers. No, I didn't say that. What did he just say? Who knows? Last night was terrible. I mean, it's the end. It's the end of the semester. It's getting there. I can't see it yet, but it's close, and I can smell it. It's getting close. And anyway, it's coming to an end. All right. So this was there are, how many questions are there in this at the end of this chapter? There are 11. Okay. We have a few minutes. We're not going to do them all. We'll do a few of them today, and we'll do the rest of them on Tuesday of next week. And we'll get into chapter 4 next week. And we'll do chapter 4, and we'll do the problem in chapter 4, and we'll call it a day. All right? But these are not hard. Okay, determine the output peak voltage. Okay, so what do we have here? What is the peak voltage for this guy? All right, so this is number 1. So we've got a volt secondary is equal to 12 RMS. That's a clue. Okay. So the R load is equal to 50. The C is equal to 1500 microfarads. Okay. So it says determine the peak output voltage, V peak. Okay. So 12 volts RMS. Okay, so it's equal to what? 12 times what? 1.414, or the square root of 2, minus 0.7. So what is that? Anybody else get 16.268? So that's my V peak. All right. So that's the value at the peak. Now, problem number 2 says what? Sketch the voltage, figure 3.2 with and without the capacitor. Okay. Without the capacitor, it shows as 16.268. It doesn't show a frequency, but that's the peak. Okay? Now, with the capacitor, we have an R load. Okay, so what would be our RC time constant? 50 times 1500 times 10 to the minus 6th. So what is RC? So it's 75 milliseconds. And it doesn't tell us does it assume 60 hertz? Does anybody see anywhere in there it says 60 hertz? Do we assume 60 hertz? Probably. So if it's 60 hertz, what's the distance from here to here if it's 60 hertz? 1 divided by 60 is what? This is my frequency. What would be what would be the period? 16.6, right? So it's 16.6 milliseconds from here to here. So from here to here, from here to there is what? It's 16, it's 3/4. From here to there, it is what? It's 3/4 of 16.6. Or it's 12.45 milliseconds. So from the peak to when it starts again is 12.45 milliseconds. Okay. So what would be the decay in in 75 milliseconds? So let's see it. We've got what would be what's our RC? What's our RC? It's a decay like this, right? It's 16.268 e to the minus what? R T over RC. Okay, so what would be the decay in 12.45 milliseconds? I guess that's what he's asking for. I don't really know what he's asking for. What is the decay in 12.45 milliseconds? We'll have to figure that out because it's 16.268 e to the minus 12.45 over 75. So what is that? Oh my. Okay, it goes from 16.268 down to 13.77. Everybody get that? Or thereabouts. Any questions, any comments? Does everybody see what I just did? If that's the way he wants to work it, I guess that's the way we can do it. Now, that's why, these are not well-stated problems. That's why it's a free book, by the way. He didn't put every little, he did all this stuff on his own, and he missed a few things. This is one of the things he probably missed. So, any questions about that? Any thoughts on that? Everybody see how that's done? This is a RC time constant question, is all it is. 3 and 4, same thing. I'm gonna let you work some of these on your own. 5 and 6, same thing. 7, what is this? This is a clipper and a clamper, by the way. So Why did he all of a sudden float in number 7 a sinusoidal question, a sinusoidal, why in number 7, and you can do 3, 4, 5, and 6. I'm not going to worry about those. You can do them yourself. But number 7, why did he put this in instead of something else? Because that's the peak voltage, isn't it? 10 is the peak. So that's what he wanted to give you. He wanted to give you V peak is equal to 10. He wanted you to have to do that on your own. Now here, this clipper is at 8. So now we've got a circuit that has an R, it's got an AC circuit, and we've got an R, and then we've got a diode, and then you've got a voltage here that is a blocking voltage at a certain point. So it's blocking at 8 volts. So as long as this is higher than that by what? 0.7 volts. So if I'm higher than 8.7 volts, this is going to work. Otherwise, it's going to what? Block. So as this signal does this, this is going to either have the effect of blocking it or letting it through. Any questions about that? So when is it allowing it through? When it is above 8.7, right up here. When it is below that, it's going to be what? What's the voltage output going to be? It's going to be blocking it, so the voltage of the output will be the same as voltage of the input. And when it's at 8.7, it's just going to be it's going to be at 8.7. Okay, it's voltage. When it's above 8.7, it's going to clip it. Okay? It's going to stop, and basically, when it's above 8.7, you're going to have voltage across this. So what goes away here comes up here. Any questions about that? So above 8.7, you're going to get this clipping. It's going to look like this. Goes up. It's not conducting, not conducting, not conducting. At 8.7, it starts to conduct, and it's flat. The what's left over goes over here. You start to conduct. Then it comes below 8.7, and then you go like this, and you're down here, and you do this, and all this kind of stuff. This is your clipper. This is the clipper. It clips off the voltage above 8.7. Why would you ever do this? I don't know. These make good test questions. It's all I'm telling you. And that's why I warned you that in this situation, all you got to do is take these questions, these few questions, and write them down exactly. And then if I ask the question, I'll ask the question, but with different numbers. But you can figure that out very quickly. But the answer to this question is right here. Okay? Any questions about number 7? All right. Number 8. All right, number 8. So this is another one. It's a clipper, but this one is what? This looks like it's in the backwards direction, doesn't it? Okay. So again, 10 volts, peak, AC waveform. this is my R, and this is my diode, and this is backwards. In other words, this is pointing down when it's at 5 volts and the 10K. Now, what happens here? Well, when we're less than okay, so we got to think about this one for a second. So when it goes negative, so this one, when it's positive, just floats along because it doesn't conduct. It doesn't conduct until we get less than what? 27 volts in the negative direction. So it goes to plus 10, just peachy. When it gets less than 5.7 in the negative direction, when it gets less than 5.7, this conducts. At that point in time, what happens? It starts to conduct and current starts to go through the 10K resistor. Not fun, but doable. Any questions about that one? Can this go to negative? Can this go less than negative 5.7? Yes, it could go to minus 10. That's what an AC waveform does. It goes from plus 10 to minus 10. And when it goes to less than 5.7, this conducts. It flows this way. It's like this. At minus 10 volts, this is like this. It's backwards. It's backwards. 10 volts. And this is 5.7. What's the voltage up here? It's 10 minus 5.7, or it's minus 4, whatever. But this actually is conducting, and this will allow flow. This is overpowered by this, so you get flow. This is bigger than this, therefore this will work. And it works until you get to 5.7, and at that point in time, this balances out and this stops. Any questions? These are not easy, are they? They're subtle. They're just, maybe you think, maybe your mind is, I don't know where your mind's at, but these are not easy, in my opinion. But my warning to you is, take them at what they are. They're not hard questions. They're just, whatever. So you can do these. My advice to you is to do what I just said. Keep a notebook on these, and every one of them that you see, write them down. Now, what do you think about number 9? If you had one that was in the forward direction, one is negative direction, now what do you got? One is both in the forward and negative, so you got a clipper that clips both ways, right? And that's all this does. It clips at this one, it clips at this one, so you have, can you automatically draw the signal for the output for this one? You go up a little ways and you clip, and then you go down a little ways and you clip, and you go back up a little ways and you clip, and you go down a little ways and you clip. And you're right, that's exactly what it is. Now, what are the values of those? Well, it's this minus this plus 5.7, this plus 5.7 in the reverse direction. Okay? Whatever that is, that's it. And this is a clamper. Gotta watch how you say that, but this is a clamper. Okay, so this was a clipper, this is a clamper. Number 10. I'm going to stop here and we'll pick this up in number 10 on Tuesday of next week. Okay, so everybody's got enough stuff to keep. Do you have enough stuff to keep you busy? Any You all set? I will see you on Tuesday of next week.